This problem is related to the concept of first law of thermodynamics, and it also uses the idea of internal energy of a mixture. Now we have been given a closed container, and inside this closed container we have two gases. One is monatomic, another is diatomic. So for monatomic gas we have 2 moles, and gamma for this is given, that is 5/3. So gamma is what? Cp by Cv, the ratio of molar heat capacity at constant pressure divided by molar heat capacity at constant volume, and this value is 5/3 for monatomic gas, and this has been given. Now we have 1 moles of diatomic gas, and gamma for this is also given, that is 7/5. So we have a homogeneous mixture of these two gases, monatomic gas and diatomic gas, and we have been given gamma in both cases, that is Cp by Cv. So this is V, so there is a typo here, Cp by Cv. Now this mixture of gases behaves like an ideal gas, individually also they behave like an ideal gas. And in the question it is given that the gas mixture does a work of 66 joule when heated at constant pressure. So when this gas is heated at constant pressure, this gas does a work of 66 joule. Then we have to find change in internal energy, that is delta U. So what is the value of delta U? So let us try to solve this problem. I will first find expression for Cv of mixture. So let us try to see. Now if you remember, that is Cp minus Cv equals to R, that is molar heat capacity at constant pressure minus molar heat capacity at constant volume. The difference of these two quantities equals to gas constant R. And we also know that Cp by Cv is equals to gamma. Now from this equation I can write Cp is equals to R plus Cv. So I can plug this value, that is R plus Cv. So this is equals to gamma. So from here I can solve for Cv. So if you solve for Cv, this will be R by gamma minus 1. So this is a expression that basically relates Cv with gamma. Now for monatomic gas, gamma is given. If you remember, this was 5/3. So we can calculate Cv for monatomic gas. Let's call this is Cv1 for monatomic gas. So R by 5/3 minus 1. So this is 3/2R. Similarly, I can calculate Cv for diatomic gas. In this case, this gamma will be 7/5. So this will be 5/2R. So now I know molar heat capacity at constant volume for monatomic gas and at constant volume for diatomic gas. Now what is the internal energy of mixture? Mixture contains two gases, monatomic and diatomic. So internal energy of mixture will be internal energy of monatomic gas plus internal energy of diatomic gas, because energy I can always add, it's a scalar quantity. So energy of total, internal energy of total thing is equals to internal energy of individual things. Now this is internal energy of monatomic, and this is internal energy of diatomic, and this is internal energy of mixture. And internal energy is given by formula NCV dt or NCV delta T, change in internal energy. Now in this case I can write internal energy of mixture is equals to NCV, and Cv will be mixture Cv times delta T. And what is the total number of moles of mixture? That is N1 plus N2. Now this side, that is internal energy of monatomic, that will be N1 Cv1 times delta T, and this will be N2 times Cv2 times delta T. Delta T I can cancel, and I can write Cv mixture is equals to N1 Cv1 plus N2 Cv2 divided by N1 plus N2. This means I know if I know Cv1 and Cv2 and N1 and N2, then I can calculate Cv of mixture. So let us calculate this. In the problem it is given that N1 is equals to 2 mole and CV1 we have just calculated, that is 3 by 2R, and N2 is given, that is 1 mole, and CV2 be calculated, that is 5 by 2R, and this is 2 plus 1, that is 3. So this will give you CV of mixture, that is 11 by 6R. Now in the problem we have been given delta W at constant pressure. At constant pressure delta W, I can write P times dV, and I can take P outside of the integration because this is constant. So at constant pressure, if I can also use PV is equals to nRT, I can differentiate this equation. P is constant, differentiation of V is delta V, N is constant, R is constant, differentiation of T is delta T. So this thing I can also write P delta V is equals to nR delta T, and delta W is 66 joule, and total number of moles of mixture is N1 plus N2, and R is the gas constant and delta T is delta T. Now we have to find delta U mixture. So this is the equation for work done, because P delta W is equals to P dV and P dV is equals to nR dt. So simply I have plugged this here and we equated with delta W. So this is my first equation. And the mixture delta U, I can write this expression, that is N1 plus N2 times CV mixture times delta T. Now if I divide these two equations, then I will have, if I divide this by 2 by 1, so this is delta U mixture divided by 66, and this side I will have, this delta T will cancel, so I will have N1 plus N2, that will also cancel, CV mixture divided by R. So if I take 66 this side, so I will have delta U mixture, and this is equals to 66 times CV mixture divided by R. So this is what we have to calculate, and CV mixture we already know, that is 11 by 6R. So if I plug this value CV mixture, that is 11 by 6 times R, I can get the delta U mixture. So let us plug this value. So this is 66 times this value, and CV mixture is 11 by 6 times R cancels out, and then 6 will cancel 66 by 11. So 11 times 11 is 121 joule. So change in internal energy of gaseous mixture, which is a homogeneous mixture, is basically 121 joule. So we equated the first law of thermodynamics. We also use the idea of, in this problem we use the idea of change in internal energy of mixture, and how we can differentiate the ideal gas equation if the pressure is constant. So this is the idea that I used in this problem. I hope you enjoyed this problem, and if you like my videos, please share with your friends, like on my channel and subscribe to my channel. I will see you in the next video. Thank you.